Hello, my name is Leon and I am a senior at UCLA. I conducted the research I'll be presenting today as part of the Research Experience for Undergraduates program at my university. At the outset, I would like to give special thanks to Dr. Kang Wang and Dr. Huan Huang for their guidance over the course of the program. My research group is part of the STAR collaboration, which performs high-energy heavy ion collisions at the relativistic heavy ion collider. Relativistic heavy ion collisions create a novel state of matter called the quark-gluon plasma, QGP for short. QGP exhibits many unique characteristics, one of which is the vacuum transition. During vacuum transition, chirality is not conserved, meaning that the QGP could have an excess of left or right-handed particles. At the same time, the positively charged spectators produce a magnetic field B perpendicular to the reaction plane, and this magnetic field aligns or anti-aligns the spin of the quarks depending on their charge. Since the momentum of a quark is also aligned or anti-aligned with its spin, depending on the chirality of the quark, this leads to charge separation away from the reaction plane. For instance, if the vacuum transition resulted in an excess of right-handed particles, then the momentum would tend to follow the spin direction, and we would have positive quarks going up and negative quarks going down, leading to charge separation along the magnetic field, and this is what we call the chiral magnetic effect, or CME. To quantify the CME, we use the gamma correlator, which is defined as the expectation value of the cosine of phi alpha plus phi beta, each subtracted by the angle of the reaction plane. Here, alpha and beta are any two paired particles, and phi is their azimuthal angles. If you expand the cosine, you get v1 alpha times v1 beta minus a1 alpha times a1 beta, plus some background effects that tend to cancel out. Here, v1 and a1 are just Fourier coefficients to the Fourier series of dn d phi. v1 is the coefficient of the cosine term, so it quantifies in-plane flow. a1 is the coefficient of the sine term, so it represents separation perpendicular to the reaction plane. And that is what we're interested in. Then we subtract gamma for opposite sign particles by gamma for same sign particles to get delta gamma, which is our measure for charge separation. Charge separation by itself isn't sufficient to prove the CME. There are potential sources of charge separation besides CME, which we collectively call background. One of the major sources of background is the resonance decay of some particles into oppositely charged daughter particles. The top graph here shows the number of opposite sign particles minus the number of same sign particles normalized. As you can see, there is an excess of opposite sign particles, with peaks in the graph corresponding to peaks in resonance decay. The amount of decay varies with the invariant mass of the parent particle, so we can graph delta gamma versus invariant mass to examine contributions from decay. In the real world, it is impossible to completely separate signal from background, so we turn to various models. The Anomalous-Viscous fluid dynamics model models CME as perturbations on top of flow-related effects by solving several fluid dynamical equations. The strength of the CME in each simulated event is determined primarily by the time evolution of the magnetic field and the extent of the chirality imbalance, which is quantified by the axial charge density. The ABFD model also takes into account background effects such as resonance decay, and it allows us to simulate events with and without CME so we can quantify the contributions from CME and from background, particularly from resonance decay. Here are the results of the simulations. For each graph, we plotted delta gamma versus invariant mass in two frames. Red is the lab frame and blue is the rest frame. On the top left, we have the pure background scenario, where CME is turned off in the simulations. We can see that there is some charge separation from background. In the middle, we have a simulation with weak CME. And in the top right, we have a simulation with strong CME. If we subtract the pure background scenario from the other two simulations that have CME and background, we get the plots on the bottom. And these should show only the charge separation induced by the chiromagnetic effect. We can draw a few conclusions from these results. We can see that the resonance background is stronger at lower invariant mass. We can also see that, at least within the ABFD model, the CME-induced charge separation increases with mass. Finally, we can use the results of these simulations to help us in our search for the CME.